You're thinking, yeah, of course it's easy for you. It's hard for me, you know. Wait. Until you see what is Laplace transform, you'll fall in love. It's invented by the Frenchman Laplace.
Yeah, I wonder what was he thinking when he invented it.
Okay. Before I can introduce to you Laplace transform, I would like to introduce to you that in your set of data sheet, at the I think the back part of your data sheet, you get to see the Laplace table.
Blur. I thought my camera blur.
Right, these are these of Laplace table. The one I'm going to use is x dot and x dot dot. So what I'm going to do is copy down. If I take the Laplace transform of x dot, this is what I get. If I take the Laplace transform of x dot dot, this is what I get. So I'll write it down.
Where you want?
So from data sheet, if I take Laplace transform and I indicate Laplace transform using this letter L in that way. Alright. So you'll find that the pace that we have today is actually quite slow. Over time, I'll build up this pace to neck breaking speed.
Luckily got video. A bit awkward, I put my camera.
Why do I do that? Because in the exam, 3 hours paper, sorry, not sure about this year, they changed. In the exam, you'll find that there's always very limited time for you to attend. So I'm going to teach you how to fit this in. The amount of allocated time to you is very short. How to do within a short period of time all the questions that you need to do. We start by using short form, Laplace transform L. So if I were to use that table that you saw just now, Laplace transform of x dot dot, right, you can refer to your data sheet as well. In fact, you need to know it very well. Capital X, S, minus S, X. At time 0, minus velocity at time 0. Just directly copying from your data sheet. So we know that the initial conditions says that this part here is equal to 0. That's our initial condition. So I'm going to simplify this as squared, xs. This xs over here means that your capital X expression is in the x domain. Why is that? Actually, if I were to explain that, it goes to mathematics already. You should be prepared by now. What is S domain? Right? If you have not, revise. Minus S, X at time 0. Or, for the matter of fact, when X at equal to time 0, I like to start to use shorthand. The shorthand that this is x naught. Right? That was from your initial conditions. When x at time 0, that's equal to x naught. If I take Laplace for x, then it just simply capital X. Yes. Okay? This part is not written in your data sheet, but then it's so easy. Laplace of x is capital XS. So what we do next is to take Laplace transform of this equation A. So if I were to do that, if you remember equation A, that's mx dot dot plus kx equal to 0. So taking Laplace transform of that x dot dot, then I get s squared xs minus sx naught, right, from this expression, plus k and Laplace transform of small letter x gives you capital letter xs equal to 0. So I'll multiply m inside, I get m s squared xs minus m s x naught plus k xs equal to 0. So there's a common factor. I'm going to underline it, xs. So I'm going to bring them together. ms squared plus k xs minus, or I'll bring this term to the right hand side, equal to ns x naught. So I can express capital XS as a subject now. That will be equal to ms x naught divided by ms squared plus k. So I'll bring up this constant x naught and then divide the numerator and denominator by n. So divide this by n, divide this whole thing by n. Then I get s over s squared plus k over m. Yep.
But then k over m can.
So you can see a few steps. Right? I divide numerator and denominator by m, so that m will be gone, this m will be gone, and this k will be divided by m.
Yes. Got the answer already. K naught.
And then that x naught, I'll just bring it out.
Laplace transform again.
So I have this expression.
Because you get this one right, k over m right, which is w naught square root of k
So this
over m,
is
correct?
xs.
You do the formula.
The next thing that I need to do is to find out what is the inverse Laplace. So if you're wondering, what is inverse Laplace?
Oh, lucky I'm recording this one. You get the cosine.
So what I want you to do is to look at some of these expressions on the left hand side. Sorry, the right hand side. This expression over here. So if I have this expression, I take the Laplace, I get this. If I have this expression, I take an inverse Laplace, and I have this. So what I'm going to do next is to look at the inverse Laplace of this term over here in the bracket. Can you find over there which expression over here is very similar to this, such that after I do the inverse Laplace, you get the corresponding
Is cosine WT. Cosine? Cosine? Yes. Yes. Yes.
very similar s over s squared plus, instead of omega, is written as k over m.
Which is the square root.
So it should be that this
And
omega
is
squared is equal to
k over m.
So after inverse Laplace, then you get xt equal to x naught, and then that's your cosine. And instead of omega t, right, because this whole thing over here is omega squared. But in this case, because it's undamped response, that means no damping, so it's natural frequency. So what that means is that this term over here will be square root k over m t. Yep. Or you can just write x naught cosine omega n t. So now if you compare these two, for the first method
I think I'll do
and
the
the second method,
provided you know
they are the same.
chop chop.
Yeah. So you can use either method to solve it.
Vì chị nó lại fish nó cũng đại liao. This is
So xt equal to x naught cosine omega nt. This one actually has a special name to it. It's called simple harmonic motion, or SHM, simple harmonic motion.
FHM.
Yeah, this kind of expression. If it's sine instead of cosine, it's also a simple harmonic motion. What that means is that this system will continue to oscillate. So if I were to sketch this equation, if I were to sketch it, this axis here is time t, and this axis here is x. The intersect is 0. So if I were to sketch x naught cosine omega nt, that's how it's going to look like. And you just go on forever. Simple harmonic motion. The amplitude of this, so as this, will be x naught. Yeah. And the time that it takes from here, this peak, to that peak, time, is actually called your period of oscillation. In your notes, it used the symbol capital letter T to represent that. But over here, I'll use another symbol that's tau.
What?
Yeah, tau. It's Greek symbol tau. T-A-U. So, why do I use this other symbol? So that it's consistent with your data sheet. Right. So in your data sheet, that period of oscillation, tau n, why n? Because it refers to the natural frequency without, it refers to free vibration. This one is given as 2 pi over omega n. That's provided in your data sheet. That's your period of oscillation. So one period is equal to tau, is equal to 2 pi over omega n. So that omega n, which is equal to the square root k over m that you have seen just now, is your natural frequency. And the units for this is radians per second. If you go ahead and solve things and then forget to include units, what does that mean? Minus 1 mark. Yeah. So if that question, after solving it, you get 1 mark, but you forgot that unit, then you just give me that 1 mark back. So don't forget to put units. So let's have the definition of natural frequency, omega n. It just means that is the undamped natural frequency of a system at which it oscillates when in free vibration. So what does this free vibration or undamped here mean? It means, in this case, this expression over here, this expression, which is the equation of this line. Yeah? So this line that you can see, maybe I'll write it that way, is the equation. X naught cosine omega n t. That's the equation of that line. What it really means is that there's no decay term. How do I see there's no decay term? Well, later on we'll go into the damping condition, and that's where you see that after I perturb it, after a while it will stop oscillating because there's damping. If there's no damping, after I perturb it, it just keep on oscillating forever because there's no damping. And no damping, we say this is an undamped case. Undamped case. Over here, undamped. So there are some other expressions that you could see, like omega n is equal to 2 pi fn, where fn, I can re-express it. And in this case, the units for that is hertz. So just expressing the period of oscillation, tau n is equal to 2 pi over omega n. It's also the same as 1 over fn. So the units for period of oscillation is seconds, because the period of oscillation is the time that it takes from this peak to that peak. That's one period. So the axis is time. This is in terms of seconds. Right. So please understand what is it that you're looking at. If it's natural frequency, it's radians per second. If it's period of oscillation, then the units is in seconds. So if you're worried about memorizing some of these equations, actually we have placed it into your data sheet. So I'll come back to this page again, but just quickly showing you the data sheet. Over here, look at that. In your data sheet, undamped second order system, there is that equation. I'll come to that later. Wn is the undamped natural frequency. This was the equation of that line that you can see over here. And the period is written over here. Right? I've been trying to get Glasgow to include a subscript n, but it was a very tough task. So let's see if I'm successful with things. But this n over here is just to say it's a period of oscillation or a natural vibrating frequency. That means there's no damping. Just to indicate 2 pi over omega n. So that's what you have over here. 2 pi over omega n. Yeah. So you don't have to memorize those equations. So let's have a look at a small little example using some of these equations. So small little example where I would say that the mass is equal to 0.5 kilograms. Let's say the spring constant K, something that I can work out. X naught. Let's try to do some measurement. So let's imagine there's a spring and there's a certain mass for this spring, and this spring under its own mass will get extended. So that mass of the spring is 0.5 kilograms. We can use the expression of F is equal to Kx, where my force over here I consider it as mg because of the own weight of that spring. So expressing this, re-expressing this, K is equal to mg over x. I want to find out what is the spring constant of that spring. So I would know that this mass is 0.5 kilograms. Gravitational pull is 9.81 divided by x. X the amount that it extended. So what I have over here is a spring. And this spring, yeah, how heavy is this?
Very heavy.
Yeah, about half a kilogram.
Ooh.
So, half a kilogram. I want to find out what's the spring constant for this. So what I'm going to do is that I'll see how much it will extend when I drop this down, alright, because it has its own weight. So what I've done is that I bring this measuring tape. So you can help me to measure.
Can help me to measure.
Hold on this. Probably you need to stand up because this string is going to get extended down quite a lot.
What the?
So how long do you think that is?
Very
Yes, roughly.
taller than you. Recording that.
About 95 centimeters, right? So in terms of meter, that is about 0.95 meters.
I literally do that.
0.95 meters. So I can do the calculation, but before that, omega n, as what we are saying before, that is the natural frequency of that spring, is equal to K m. So K over here is actually mg divided by x, and then divided by m. So this m and that m can get cancelled. Right. So what I'm left with is square root of g over x. And g is 9.81, and that x 0.95 square root. Can somebody calculate what is the value of this? Actually, I don't know. It's live demonstration. What's value?
I was calculating.
3.21, so it's about 3.2. And the units? Natural frequency?
Radians per second.
Radians per second. Yeah. If you say hertz, then I take back one. So what I'm interested to find as well is the period of oscillation. So that is 2 pi divided by omega n. So that's 2 pi divided by 3.2. And what do I get for this? That is 1.96 seconds. Yeah. So let's see if it's true. So what that numbers mean 1.96 seconds, which is close to about 2 seconds here. That means if I can drop this, it comes back is one oscillation. So one oscillation, period of oscillation should be about 1.96 seconds. So now if I will drop this and let it oscillate for 10 times, and then And one of you help me to use a stopwatch and record. How much time is that?
No stopwatch function.
You have a stopwatch? Is that a stopwatch? Okay. We're gonna let it drop. And then we're gonna count 10 cycles, yeah? So I'll repeat. Is 1, 2, and then we do it until 10. So at 10 cycles, or 10 oscillations, and you tell me how many seconds. We take that number, divide by 10, and then it should be close to 1.96 seconds. Yeah, it makes sense. Okay. So, ready? Give me a trial. I hope I'm tall enough. Okay, I'll try not to move my hand. So at the count of 3, 2, 1. 3, 2, 1, stop. 3, 4, 5, 6, 7, 8, 9, 10.
18. 18.
18.27. 18.27. 18.27 seconds. Divide by 10, I get 1.82 seconds. Close enough.
I finished. No, I cannot afford to see the.
So some of you will be wondering, hey, why isn't it totally equal? Well, there's some losses, right? Yeah, there's some air friction. We're talking about this case where it's an undamped system, no damping, but obviously there's some air friction as it's oscillating, right? So because of that, then the kind of time that you can have is slightly smaller. It's close enough for a quick and dirty way to figure out if the theory is correct. Okay, going back. We had this expression mx dot dot plus kx equal to 0. So what I'll do next is to divide throughout by m. So I get x dot dot plus k over m x equal to 0. Now these are not any equation. These are very specific equations here. So please know that this is so specific that we call it homogeneous second order linear differential equation. So this is the case where there's no damping. Later on, we'll develop a case where there's damping and this equation will start to change. But if you see this equation, it's for the undamped case. So this term over here is actually your omega n squared equal to 0. So this expression available in your data sheet. Where is it? I'll just quickly go over. Right over here. Alright, so you don't have to memorize that. So this expression now is going to say that this equation of all undamped second order mechanical system. Undamped here means no damping. That's to say, if I were to oscillate things, right? Let's say, for example, this microphone over here, if I oscillate it, my purpose go up and down. Yeah. If it continues to oscillate, this is the case. The equation for that is written over here. or mechanical systems that oscillates without any damping. So now you feel safe. This world is a control world. They follow certain kind of mathematical law. Let's have a look at an example. And how I'm going to write example would be WE, and in this case 2.2. What is WE? WE is your work example. Work example 2.2, right? So I'll write WE 2.2. I'm going to solve this question over here. So if you have not read that question, which is shame on you, yes, you should read before coming to lecture. Okay, after the shaming, we'll continue to work hard. I'll sketch that question in this figure. We have the mass that is supported on a board, and that board, that's a springy board, can be represented by a spring constant. And it has this datum. So that model machine we model this machine as a point mass, and this point mass M is 500 kilograms, that's given in the question. And then we'll try to model this flexible wooden floor as a spring. And the spring would have a stiffness or a spring constant that we call K for now. So in your exam, when it comes to solving questions, you need to provide the free body diagram. Yeah? So sometimes I use a shorthand free body diagram. Free body diagram. FBD, very popular word. So how to develop that free body diagram? It's like what we have seen before. Cut that spring. So what you're going to have is that you have the mass, and then the spring has been cut in that way. So the kind of spring forces that you experience F is equal to K, and I'm going to drop that static delta for the delta static displacement. So the ST, that part, I'm going to drop it because it's tiring to write so many times. Right. This is the case for static condition. Right. That's why you have the delta over there. So if I just focus on this part, just this part, the figure that I'm going to get will be, there'll be M, that's the datum, there'll be that force. I think I have the arrows wrong. These arrows are wrong. And I'll tell you why it's incorrect. Right. Now, if you were to have this mass resting on this wooden board, wooden floor, that spring will be under compression or extension. Compression. So once I know that it's compression, I'll do this to the spring. The forces compress. Right? So these are the steps that you need to go through. And then after you have this arrow that's going downward and this one upward to compress the spring, then you have the equal and opposite force. That's how you establish it, equal and opposite force, because of Newton's third law of motion. So that means this force is actually pressing upward. That's your F is equal to K sigma, or K delta, sorry. And then this mass here would have the point mass mg that's pointing downward. It's a gravitation pull. So for static condition, you'll be summing up the forces along the x-axis, because static condition equated to 0. So let's say you have this force mg that's pointing downward, so it's a positive value. This spring force is pointing upward against my convention datum x, then it's minus value, and k delta equal to 0. So in your question, you're actually given the static displacement with a certain value. So the static displacement in this case is 1.2 millimeters. It's written in that question. 1.2 millimeters, how many meters is that? I'll just write 1.2 times 10 to the power minus 3 meters. Because in calculator, you type it down that way too. So I'm going to make use of this. Got to say that the question is actually asking what is the natural frequency, and they want it in revolution per minute. So this revolution per minute is another way to express radians per second. Later on, I'll do the units conversion for you. In fact, I was discussing with Glasgow, saying that can you stop using this imperial units revolution per minute, because we are used to SI units radians per second. So in the exam paper, when I review it, I change it from revolution per minute to radians per second, and then when they print out the exam script, they change it back to revolution per minute. So I think you're having a overseas university degree program, so you're going to learn that way, right? Imperial units, revolution per minute. But no problem, I'll teach you how to do the conversion. So that spring constant, which again was mg divided by the amount of static displacement, delta, that will be 500 times 9.81 divided by 1.2 times 10 to the power minus 3. If you work this out, 4.09 times 10 to the power 6. And spring constant unit is newtons per meter. That's for the static condition. Let's have a look at the dynamic condition, or the perturbed condition, or the disturbed condition. So in order to figure that out, you will still be sketching that same figure. So in this case, you will still have the mg. And because of dynamic condition, the force that's acting upward now, that's what you've seen in previous example. This is K delta plus X, right? So I often write this F equal to this here, but over time, you see that I will start to drop this as well. Right? This is known as the force, the one with the arrow. So you don't have to keep on writing F equal to this. So for dynamic condition, again, summing up all the forces along x equal to mass times acceleration, because dynamic, so you got to be mass times acceleration. So summing up the forces, again, we have the datum that's pointing downward. So you have mg in the same direction. This force is acting upward, so k delta plus x equal to mx dot dot. So I can go ahead and expand this out. Mg minus k delta delta minus kx equal to mx dot dot. So from this, you know that this term over here is equal to 0. So let me rewrite everything. Mx dot dot plus kx is equal to 0. So x dot dot is equal to plus k over mx equal to 0 by dividing throughout by n. And we know that this kind of expression is an undamped case, undamped natural, the undamped mechanical system. So this is the same as this expression where omega n now is equal to square root k over n. So the question wanted us to find out what is omega n. So hence we can substitute our k value in there. So k is 4.09 times 10 to the power 6, and the mass is 500 kilograms. So if you were to solve that, that will be equal to 90.44 radians per second. That's the units for natural frequency. But they wanted revolution per minute. So I'm going to teach you how to do the conversion in a very logical way. Yeah? So we wanted to change radians into revolution. Right, so I'm going to change this, change it to that. So in order to do that, what I'll do is that I have 1 radian as a denominator. So how many revolutions is 1 radian? Knowing that 2 pi, no, not half. Knowing that 2 pi radians is 1 revolution, right? 2 pi radians is 1 revolution. So 1 radians will be equal to 1 over 2 pi, right? Okay, I'm going to write this down. So 2 pi radians is equal to 1 rev. Right? So 1 radian is equal to, right? So we should not be doing this, you know, this is like somewhere very, very early on when you learn. Yeah. So this is 1 over 2 pi. And then that settles my radians. So what I've done is convert radian into revolution by having this factor multiplied. Yeah, so it makes sense. Now let's look at seconds. Change seconds to minute. So I can't put any number except 1, so that this second and second could be cancelled. But 1 second, how many minutes is that? 1 over 60. So that means 90.44, you got to multiply by 1 over 2 pi, and multiply by 1 over 1 over 60, which is 60, and then you get revolution. Yeah, very cool, right? Yeah. You don't have to memorize things at all. Yeah? It's logic. So do that calculation, and you get 863.8 rev per minute. That's the answer. Let's have a look at your work example 2.3. And there's actually a figure provided in work example 2.3. So what I'm going to do is to sketch that figure. Right. If you didn't bring or if you didn't print, then that figure is this. Yeah, here's a figure. So we're not going to kind of like cut the spring anymore, because you would know how to do it. We're going to jump straight into the static condition. But I'll do a sketch of that static condition. The question that it wants is to derive the equation of motion. Right? That's what the question wants. And then second part, they wanted us to find out what's omega n. So for static condition, I'll do the sketch. That beam has a mass mg. That pivot point is O. So the mg mass has a distance away from the pivot point, that's A. A is not acceleration, A is the length. And the whole length of this beam will be L. And at the end over here, there's actually a spring. So if you cut the spring, you'll be able to find out that actually that spring, if you think about it, is it under tension or compression? Or if you look at this figure, is that spring with the mass over here, is it under tension or compression? So tension is sketched this way, so equal and opposite force. Right? So it'd be pointing upward, and for static condition is K delta. So unlike the work example just now, this work example is a rotary system. So if it's a rotary system, then we don't sum up the forces, but sum up the moments about point O. So you have to be very clear about the system that's given to you. Is it a linearly moving thing, or is it a rotating thing? If it's a rotating thing, then your symbols that you use will be different. Right? So in this case, it's moments about point O, static condition, so moment is equal to 0. If you forgot how to go about calculating moments, so moments is actually force multiplied by perpendicular distance. Yep. And this perpendicular distance is from the pivot. So if I look at this case over here, there's a force from a perpendicular distance of A away from pivot. There's another force from a perpendicular distance L away from a pivot. So there are two moments over there. This moment is creating this direction of the torque. So this is clockwise. So clockwise, would it be a positive or negative value? We look at the convention that's given to us. Over here, it says in this direction is considered positive, this clockwise direction. So clockwise direction, that moment will be mGA and is positive value. Force multiplied by perpendicular distance A. The other moment is going the anti-clockwise direction, so you'll be a negative moment, and then force, which is K delta, multiplied by perpendicular distance L. The whole thing equal to 0. I call this equation 1. That's all for the static. For the dynamic condition, I'm going to sketch it again, and I want you to notice how I go about sketching. In dynamic condition, this beam here will be rotated downward. So if this is my data, the beam now will be rotated this way, theta. And they will still experience mg force on the beam. However, this distance over here, perpendicular distance, all the way here, this distance is the same as from here to here, right? This distance. So if you have angle over here, and if this is A, the length of the beam is A, this will be A cosine theta, right? Length. So if you have to blow it out, you have that triangle, theta, the length is A, so this is cosine, A cosine theta. So obviously here will be A sine theta. Alright, we went through this in our first lesson. So why I need that? Because later on I need to multiply the perpendicular distance. So the same is going to go for this distance over here, right? The same larger triangle. That will be not A but L, because that's the entire length of it. L sine theta. Right, that's the displacement. That means it rotated from here to here. Right? Kind of swing downward that way. And that perpendicular distance is L sine theta. So the force is actually acting upward, right? Because of that spring. And in this case, that spring force will be K delta plus this amount of extension, L sine theta. Why written in that way? Because you had seen before in dynamic condition, we used to write K bracket delta plus X, where X is that vertical displacement. Yeah. So the length from here all the way to here, this would then be L cosine theta, because this length, this one, is L. So this is going to be a bit shorter, L cosine theta. So with that, we can sum up all the moments about point O is equal to I naught theta dot dot. So this part here, why is it I naught theta dot dot? Actually, that was delivered in our first class, first lesson as well. So I just exit this page for a quick while, show you where it is. I know. Is it here? Yeah, that's fine. The moments equal to IA theta dot. Yeah, so I'm going to make use of that. Moment equal to I theta dot. So that I naught over there is moment of inertia about point O. So let's sum up all the moments. You have the first one in the same clockwise direction as our convention. Force mg multiplied by the perpendicular distance A cosine theta. You have the second one over here. That's against our convention direction. So that's minus the force K sigma plus L sine theta. That's forcefully, and then multiplied by perpendicular distance equal to I naught theta dot dot. So please don't write summation of moments is equal to NA here. No. NA is for linear motion. For rotary acceleration, or angular acceleration, that summing up moments is equal to moment of inertia multiplied by theta dot dot. Theta dot dot is your angular angle, your angular acceleration. So we know that if for small angle theta, sine theta is approximately equal to theta, and cosine theta is approximately equal to 1. So this term over here, cosine theta, approximately equal to 1. This one, theta, and this one, 1. So what we'll do is to pack up everything. So we have this part over here, that will be mgk minus, I'm going to multiply everything together. So that will be k sigma L and minus k L theta and then another L, so L squared equal to I naught theta dot dot. So I can see that this term over here is the same as the static condition. So this is equal to 0. So 1 left minus k L squared here is equal to I naught theta dot dot. Re-expressing this, I naught theta dot dot plus k L squared theta equal to 0. I want to find out what is my moment of inertia. I naught. There's actually an expression for this. The expression is mass multiplied by perpendicular distance squared. Where do I get that? So I'll come back to this page again, just referring you to your data sheet. So toward the end of your data sheet, you get to see this moment of inertia table. Yeah. This figure actually confuses a lot of people, but I want you to know that there are different point masses, and they are all in the same plane. They are all in the same plane. So if you want to find out the moment of inertia due to one dot or one point mass, then we take the mass of that multiplied by the moment of inertia, multiplied by the radius. Right. Actually, radius is not a good way to say, but you can imagine it is a spherical disk. So that perpendicular distance away from your axis, mr squared. That's the equation for moment of inertia. So in this case, we actually have that figure in a very similar way. You have that point mass, I use this, right? That point mass m, and then at the distance a squared away. So that's why we have this as m a squared. So we can divide now throughout by ma squared. I have kl squared divided by ma squared, theta equal to 0. And expressing it in the meter weight equal to 0. And that's your equation of motion. Now for an undamped second order system, and actually you can see your data sheet, that theta dot dot plus omega n squared here must have that kind of expression, right? This and this, they must have the same expression because it's an undamped second order system. So this implies that your omega n will be equal to square root of this. And this will be L over 8. So that is your expression, radians per second. Now, I kind of want to build a habit of writing square root with this little bit over here, so that you would know that I'm not encompassing this term. It's just a German way of writing, right? So I find it very accurate. You wouldn't miss out anything. If you write this way, and you're kind of like not sure if you're including or not. So
Maybe we forgot
it's a book.
forgot you.
Yeah, you can adopt this if you like.
Actually, I don't mind the chicken rice.
So next week we're going to have damping coming in. So this is a case of simple harmonic motion undamped system. Next week the equation will get a little bit more complicated, and I'll see you next Tuesday.
Hi, Maria or Dragon. Then transfer to plane E4 Wow!
Now, actually, my advice is that if you don't understand any part of concept, don't accumulate. Your exam is coming this semester. Unlike your seniors. Your seniors had it in Sem 2. Dynamics and control in Sem 2. This year, you have your exam in this semester. If you don't understand any of the concept, don't wait to come and approach me after class. If you have the attendance sheet, please pass it to the front. Thanks.